Welcome back to Chemical Process Safety. This video is about revealed versus unrevealed failures. So far in the other two videos I've done, we've assumed that reliability and failure probability assume that faults are immediately obvious and instantly fixable. But in real life, you may only be aware of a fault if you find it if you're looking for it. Also, it may take time to fix. So as an example, consider if you got a flat tire and you had to put your spare tire on, would you know for sure that it is functional? I guess most people, myself definitely included, I do not take the time every year to take my spare tire out and check to make sure that it's still okay. So in the event that it was not, that would be an unrevealed failure. Or as another example, consider a pressure relief valve. It'll only work if it is actively relieving pressure. So if it's not in action, how can you be sure that it's actually working? These are both examples of unrevealed failures. So we can think of this graph, this y-axis has a binary value of operational up here and failed down there. We can define T0 as the operational time. So as long as the thing is working in good working order, that would be T0. And once it fails, the operational will drop and it'll be failed. And this T sub R is the time that it takes for repairs to happen. Obviously, long repair times are bad, not only for the economics and making sure the process is proceeding, but also because most processes are safer when everything is working. When certain components are down, obviously, even if the rest of the process goes down, it's not good to have certain parts of our process just kind of sitting around without it being operational. So you can define the mean time between failures in this instance as tau 0, the operational time, plus tau r, the time under repair. I can average these values for multiple different events, keeping in mind that the operational time and the repair time are not going to be the same every time. The repair time might be a function of the time of year or the nature of the reason why it became unoperational or any number of factors. So this is, you sum them all up and then you divide by the number of events that you have. The availability, which is a key thing that we'll talk about, is the probability that a component is functional. And obviously for a chemical process, you aim to have all of your equipment as available as you possibly can. 100% availability is the absolute goal. So I'll define availability as tau 0, the operational time, divided by the total time. And keep in mind that these are all averages. So the average operational time divided by the average operational time plus the average repair time. And I can express that as mu times tau naught. And this is completely analogous to reliability in the last couple of videos. The unavailability then is going to be the time that it is down. So tau r over tau naught plus tau r. Or alternatively, I could say it is tau r over the mean time between failures, given what my definition for mean time between failures was up here. All right, so for unrevealed failures, in the mathematical analysis, we'll have to first assume that the repair time is negligible, so that the repair time is very, very short. But tau I is the inspection interval. So in this instance, remember, the thing has failed, but we don't necessarily know about it yet because we might be inspecting every year. And let's say something fails at 10 months, but until we get to inspect it, we don't necessarily know about it. So in this example, TI would be 1 year, and then T0 would be 10 months. At 10 months, it fails. And now it's proceeding under this unavailable length of time. The unavailability of this piece of process equipment is going to be tau u over the entire interval. And I can also express this as the integral of the probability of failure function. So remember, the probability of failure is 1 minus the reliability, or 1 minus e to the minus mu t. And if mu t is small, this is just a mathematical thing, e to the minus mu t for a small ut is just simply going to be equal to ut. So that'll simplify things mathematically a little bit. So this is my expression now for unavailability. I can now say that availability is the complement of unavailability, again, using the logic that something is either available or unavailable. It's never two things at once, and it's never neither of those two things. And I can obtain this expression for my availability. If mu times tau I is small, and what this means is that if you inspect with much more frequency than the mean time between failures, which you might say is a good thing to do, right? If your mean time between failures is 5 years and you are inspecting every 1 year, that's a pretty good safety practice. Of course, you can't overdo it, right? You don't want to inspect something that's going to fail every 5 years, every week or something like that, because there's not enough time to pay your operators or your inspection people to do that frequently. So mathematically, what you would do is you would perform a Taylor series expansion, and then you would obtain the following expression for your unavailability. If tau I, the entire interval, is much less than the mean time between failures, the component is unavailable for half of the time. So let's look at some practical examples of where I can apply this. Let's say that I have a pH meter and the reported mu value for this pH meter is 5.88 faults per year. How often should I have to analyze it if I want it to be available for 99% of the time, 90% of the time, and 50% of the time? This is a funny example to me because in my personal experience in grad school, we had a pH meter in our lab, and it seemed like every time I needed to use it, I had to fix it first because it wasn't working. Now, from my safety perspective, that wasn't necessarily a problem because I was measuring the pH of something that if it was incorrect, I just had to fix it, not the pH of something where it had to be correct or else I was going to have an explosion or a chemical release or something like that. So this could have been a much more serious situation. I just like to think back on that pH meter and smile. So again, mathematically, what we would do is we would use this formula. So I know for sure that mu is going to be 5.88, and then Ti is going to be the inspection interval. That's what I want to calculate. And unavailability is 1 minus the availability. So if it's available 99% of the time that I need it, and again, for a pH meter, you might think if it's not a huge deal, I might be willing to sacrifice the inspection time and get away with 50% availability. But if it's something truly integral to process safety, then definitely something 99% or above may be desirable. So again, I convert availability to unavailability, and that will allow me to plug it into this expression. So I just take 1/2 times 5.88 over to the other side, and I find that the inspection interval for 99% availability is 0.03 years, 0.003 years. And you should not ever report your answer like this because at a glance, I have no idea how long 0.003 years is. So I'm going to convert that to days, which is a much more sensible answer. So I conclude that if I want my pH meter to be available 99% of the time, I must inspect it close to every day or every other day, which depending on how arduous of a task that is, that may be acceptable or unacceptable. But this is a somewhat high mu value. So if the mu value were much less, obviously this conclusion would be less. So interestingly, I can do the same thing, and I can see how the answer changes for various levels of availability. If I only care that it's available 90% of the time, my answer changes to 12.2 days. Or remember, I don't know if I mentioned this, but there's two forms. This is the approximated form with the mu times Ti being very, very small. This is the more precise form. So depending on your precision, and that's what I'm doing here. So here, mu times Ti is indeed very, very small, right? Because Ti is very small. But here, Ti is larger, so mu times Ti is greater, and it's not quite much less than the mean time between failures. So for 90% availability, I need to inspect it on the order of every 2 weeks or so. On the other side, or on the third possibility is for 50% availability, I get that I only have to measure it once or inspect it every 99 days. And for this one, I use the full version because the value for TI was going to be too large here. I noticed I was starting to get some variability here. So again, this is a good example that illustrates the more important the availability is, the more frequently you should inspect something. So this is very interesting to me because it's a quantitative way of, if you're at your internship or at the lab for you're working with equipment that has to be inspected every year, you might, like I did, wonder who decided that every year would be the thing to do. Is it just because, annually makes it easy to remember? And that may be part of it, right? A regular schedule is going to make it easier to make it routine. But why every year as opposed to every month, or I don't know, every 5 years, every 10 years? It's because somebody did the math and ran the numbers and decided that for the desired availability, that a year was the recommended thing to do, whether that person was at your company or at the manufacturer or wherever. Every process component should be expected to fail at some point. And that's okay, right? It's not a problem unless it's available at the exact moment that you need it. So let's express the frequency of an episode as lambda and the number of times that it occurs as P sub D in a given time interval. If the unavailability is U, a dangerous episode is going to occur every U times PD episodes. So the frequency of the dangerous episodes, lambda D, is equal to PD times U divided by TI, and that is equal to lambda times U. If the failure rate is small or the checks are infrequent, I can express it like this, where unavailability is 1/2 times mu times TI, and lambda D is expressed in this way by plugging in the value for U into this expression. So let's say that we have an emergency system on a reactor and that's checked every month, and we expect a high pressure event every 14 months. So again, once every 14 months is when we expect to need this emergency system. If we check it every month, what is the probability that when we need it, we won't have it? So lambda is going to be the frequency of episodes, 1/14 months in this case, and the formula uses years here, so I have to convert that into years. So 1/14 is a little bit less than one inverse years. And I basically plug that into the formula, and what I get is the mean time between coincidences, MTBC, is every 50 years. So again, this is another quantitative thing that you can say that, honestly, it depends, right, on what the consequences of this high pressure event are. If it's going to be a catastrophic explosion, this thing happening an average of every 15 years may be completely unacceptable, right? We might want to see this number at 500 or 5,000 years. And that would tell us that we need to inspect the emergency system much more frequently. On the other hand, if the high pressure event simply means that the rupture disk blows and it's not that big of a deal other than that because the release components aren't hazardous or something like that, it may be perfectly acceptable. 50 years may be overkill in that situation. Maybe a mean time between coincidences being less than that would be okay. Again, it always depends, and this is interesting because it is a quantitative and objective way to approach the problem. So with that, I'll wrap this video up. Hope you enjoyed as always. I'll see you next time.